On the summit of Cerro Armazones in the desert region of Chile, the largest optical eye on the planet is gradually being completed. This is the most insane construction project in the history of astronomy. With a gigantic dome the size of the Roman Colosseum and a primary mirror nearly 40 meters wide, the extremely large telescope has the ability to collect light 100 million times greater than the human eye and deliver images 16 times sharper than the Hubble Space Telescope. When completed, it will allow humans to directly observe rocky planets outside the solar system and look deeper into the earliest period of the universe. So how can humanity build one of the most advanced cosmic observation machines in history under such harsh conditions? And how much further will this help expand our understanding of the universe? Over more than a century, each new generation of larger telescopes has opened a turning point in how humanity understands the universe. If the telescopes of the early 20th century helped us realize that the Milky Way is only one among countless galaxies, then the Hubble Space Telescope allowed humanity to look billions of light years deep into the past of the universe. But by the beginning of the 21st century, the observational limits of existing telescopes had begun to become a new barrier. For this reason, European Southern Observatory launched the Extremely Large Telescope project as a generational leap in space observation technology. The facility is being built at an altitude of more than 3,000 meters on the summit of Cerro Armazones in northern Chile, one of the regions with the best sky observation conditions on Earth. To reach this location, you must cross the Atacama Desert, one of the driest places on the Earth, situated between the Andes Mountains and the Pacific Ocean. When it becomes operational, the ELT is expected to allow scientists to directly analyze the atmospheres of planets outside the solar system, observe the formation of the first stars, and test some of the largest hypotheses about the structure of the modern universe. To achieve this capability, engineers must solve one of the most precise construction challenges in the history of astronomy. Often described as Mars on Earth, the Atacama Desert has more than 320 cloudless nights each year, humidity levels close to zero, and almost no light pollution, creating a nearly perfect natural lens that minimizes atmospheric disturbance as much as possible. For this reason, the summit of Cerro Armazones was selected as the site for the largest optical telescope ever constructed on Earth. However, before the structure could be built, engineers had to solve a task that seemed simple, but was in fact extremely demanding: creating a foundation stable enough for a machine that requires precision at the nanometer level. Originally, the summit of Cerro Armazones was only a sharp, rocky peak, completely unsuitable for placing the foundation of such a structure. Therefore, the first preparation step was to reshape the mountain itself. Engineers had to use controlled explosives to remove more than 220,000 cubic meters of rock, flattening the entire summit into an artificial plateau hundreds of meters wide, large enough to support the foundation of the largest ground-based observing structure ever built. As soon as the site had been leveled, another harsh physical challenge emerged from deep beneath the ground. The summit of Cerro Armazones lies entirely within one of the most active seismic belts in the world, where Chile experiences on average more than 600 earthquakes each year. For a highly sensitive optical machine that requires precision at the nanometer level, even a small vibration transmitted from the bedrock would be enough to misalign the mirror system and completely compromise the billion-dollar project. To overcome this obstacle, engineers had to create a foundation that is almost isolated from the Earth itself. The entire telescope structure is placed on a massive concrete foundation approximately 80 meters in diameter, beneath which multiple layers of vibration isolation materials are integrated to continuously absorb movements from the surrounding environment. This system works like a giant shock absorber, helping isolate the observing structure from even the smallest vibrations rising from the mountain below. In addition to that, engineers also had to precisely control the thermal expansion of the foundation according to the day-night cycle of the Atacama Desert, where temperatures can change very rapidly within just a few hours. This required the entire foundation structure to be designed to maintain geometric stability with an error margin close to zero. Only when the foundation achieved this near-absolute stability could the project move on to an even more massive stage, constructing the enormous protective dome, a mechanical shield designed to protect the entire telescope from desert winds, temperature fluctuations, and the harsh environment at an altitude of more than 3,000 meters. An optical machine operating at nanometer-level precision cannot function reliably amid the violent winds and extreme temperature differences of the Atacama Desert. For this reason, the entire telescope must be enclosed within a massive steel dome, a mechanical shield that fully controls the observing environment surrounding the most powerful eye on the planet. With a height of 80 meters and a diameter of 90 meters, constructing this superstructure is like assembling a giant set of Lego blocks. Steel modules weighing up to 70 tons each were transported piece by piece to the summit of Cerro Armazones using precisely controlled specialized vehicles, and were then assembled by heavy-duty cranes with tolerances measured only in millimeters. However, this is far from being a static enclosure. The total weight of the dome reaches 6,100 tons, including two enormous sliding doors weighing 400 tons each. To ensure that this massive structure can withstand the strong winds that frequently occur at an altitude of more than 3,000 meters, the entire design was tested under extreme wind tunnel conditions. The shape of the dome was optimized to deflect airflow around the surface, rather than allowing it to strike directly at the center of the structure, keeping the observing environment inside completely stable. And the most remarkable feature is its ability to rotate 360 degrees to open the telescope's field of view, supported by a giant rail system consisting of 36 specialized wheel assemblies, each weighing approximately 20 tons. This system allows the dome to move smoothly in alignment with the observing direction of the telescope inside, while still maintaining mechanical stability at a near-absolute level, a mandatory requirement for the most precise optical instrument ever built by humans. During observations, the ELT cannot remain stationary even for a single moment. To lock onto the faint light from exoplanets located many light-years away from Earth, the entire telescope must continuously rotate with the motion of the sky, rotating horizontally in azimuth while simultaneously adjusting its viewing angle vertically in elevation with near-absolute precision for many continuous hours. To achieve what seems almost impossible, engineers placed the entire telescope, weighing approximately 4,600 tons, on a giant azimuth rotation system nearly 50 meters in diameter, one of the largest precision tracking systems ever constructed in the history of astronomy. What is remarkable is that the entire telescope structure does not directly contact the metal rail system beneath it. Instead, it rests on massive rotational supports, where an ultra-thin hydrostatic oil film is continuously pumped under extremely high pressure between the contact surfaces. This fluid layer lifts the entire structure off its base, almost completely eliminating mechanical friction. It not only allows the enormous steel structure to move with extraordinary smoothness, but also acts as an advanced damping layer that absorbs nearly all vibrations generated by the drive motors. Thanks to the near-absolute stability provided by the giant hydrostatic tracking system, the ELT structure was finally ready to support the heart of the entire project, the primary mirror system M1. With a diameter of 39.3 meters and a surface area of nearly 1,000 square meters, this enormous eye has a light-collecting power approximately 100 million times greater than that of the human eye. However, casting a single monolithic mirror at this scale is physically impossible. For this reason, engineers designed M1 as a giant honeycomb-like matrix composed of 798 hexagonal mirror segments, each measuring approximately 1.5 meters across, manufactured from Zeradur, a glass ceramic material with nearly zero thermal expansion under the temperature variations of the Atacama Desert. However, the greatest challenge did not lie in manufacturing each individual mirror segment, but in making all 798 segments function as a single optical surface. To achieve this, beneath each segment is an ultra-precise actuator system capable of continuously adjusting its position along 3 spatial axes in real time. Laser sensors measure misalignments between the segments with extremely high accuracy, then transmit signals to the central control system to correct the shape of the entire mirror surface thousands of times per second. Thanks to this mechanism, the entire M1 operates as a single enormous mirror with a light collecting area larger than that of any optical telescope ever built before, allowing the ELT to gather tens of times more light than previous generations of ground-based telescopes. And when this giant mirror begins to collect the faint photons that have traveled across the universe for billions of years before reaching Earth, the ELT finally possesses the most essential capability of any telescope: the ability to truly look deep into the history of the universe. After converging at M1, the beam of light is reflected upward to the secondary mirror M2, suspended at a height of 60 meters, then passes across M3 and proceeds directly into the technological heart of the project, the deformable mirror M4. To defeat atmospheric turbulence, the critical weakness of all ground-based observatories, M4 is designed as an optical membrane measuring 2.4 meters across but less than 2 millimeters thick. Suspended on more than 5,000 magnetic actuators and guided by a real-time laser measurement system, the surface of M4 continuously flexes and deforms 1,000 times per second to perfectly compensate for every distortion in the incoming light. Finally, this purified beam is stabilized one last time by mirror M5 before being transmitted to the scientific instruments. It is precisely this five-step reflection chain that enables the ELT to become effectively immune to Earth's atmosphere, ready to dissect the universe with a level of resolution never before achieved in human history. The purified light arriving from the mirror array is, in fact, still only raw signals. To truly interpret the messages from the universe, the ELT requires a suite of advanced observational and analytical instruments at the final stage, where photons, after traveling for billions of years, are measured and converted into scientific data. One of the most important instruments is Mikado, the first extremely high-resolution infrared camera of the ELT, designed to capture detailed images of early galaxies and to directly observe exoplanets at very large distances. Alongside it is Harmony, an integral field spectrograph that separates light into different wavelengths, allowing scientists to analyze the chemical composition of stars, gas, and even the atmospheres of exoplanets. The next key component is METIS, a system dedicated to observations in the mid-infrared region, enabling the study of planet formation and the structure of material around young stars, regions that were previously almost beyond the reach of ground-based telescopes. All of these advanced instruments are installed on ultra-stable observation platforms behind the primary mirror system, where each device must operate under conditions in which temperature, vibration, and geometric deviation are controlled at extremely low levels. Only when these instruments operate in full synchronization with the adaptive mirror system and the high-precision tracking mechanism does the ELT truly become a complete scientific machine, ready to decode the deepest mysteries of the universe. When all mechanical and optical components are perfectly synchronized, the ELT will reach the most important milestone in the life cycle of any observatory: first light, the first arrival of light. Planned for the year 2028, the entire massive system, from the 80-meter-tall steel dome, the nanometer-precision hydrostatic tracking platform, and the primary mirror composed of 798 segments, to the chain of adaptive mirrors from M2 to M5 and the observational instruments, will operate together for the first time as a single unified machine. Photons that left distant galaxies billions of years ago will finally converge on the surface of M1 and be transformed into the first scientific data in the history of the ELT. This will not only mark the completion of a structure, it will be the moment humanity opens an entirely new way of seeing the universe. Right now in the harsh Atacama desert, thousands of engineers and scientists are still racing against time to complete this monumental megastructure. It is not only the pinnacle of ground-based mechanical and optical engineering, but also a launch platform for humanity to answer one of the greatest questions of all. Does a second Earth exist, hidden somewhere within the Milky Way? Thank you for joining Mandarin Tech on today's journey exploring the extremely large telescope. Don't forget to press like, subscribe, and turn on the notification bell so you won't miss the next mega project technology stories.